Good morning. Good afternoon.
Good afternoon. This is Umakant here. Hi.
Hello, Umakant. This is Mark here. Should I try and share my... Hi, I'm good, thank you. So it's early evening over there, yeah?
Yeah, it's 6:25 p.m. Yeah. Professor Bhanudas is here. Just a moment. Professor Das.
Maybe I'll just try and share my screen and make sure that's all good.
Yeah, sure.
Okay. You see that okay?
Your screen?
Yes. Do you see my first slide? Oh, sorry, no, I have to share. Yeah, not yet. Yeah. 1 second. Yeah. 1 second. How's that?
Yes.
Yes, we can see.
Yeah, we can see it now. Yeah.
You see my laser pointer?
Yes.
Okay, great. I'll just turn it off for now and then I'll put it back on.
Okay, so hello, Professor Saffman. I'm Bhanu Das. Okay, yeah. Nice to meet you.
Nice to meet you over the video.
Yes, over the video. Yes, I mean, I think I probably met once in China, I guess, a long time ago, maybe 4 or 5 years ago, I guess.
In Wuhan, I guess.
Exactly. Yes. I mean, okay. So thank you for accepting our invitation and giving a talk, at a, which must be early morning your time. I mean, thank you so much. Okay.
You're very welcome. My pleasure.
Okay, thanks.
Okay. So there will be a couple of talks today, and then tomorrow and the day after, most of the conference.
Yes,
yeah.
I think your talk and Professor Omori's talk is today, and the rest of the talks will be tomorrow and on the 28th. So.
Great. And, because of time schedules, I won't be able to attend all these talks, but it will be on YouTube, so I can go back.
Yes. So yeah. Yes, we'll send you all the recorded talks that you miss. So
great.
So we'll have all the talks. Yes.
That sounds great.
Okay.
Okay, so maybe I'll just put my screen back on to be ready.
Okay. So have I been made a co-host, Umakant? Okay.
Yes. Yeah, you are co-host.
Okay. All right. Okay. So, Professor Saffman, it's 45 minutes plus, I think, 10 minutes of, question answer. So it'll be, discussion for about 10 minutes.
Sure, that sounds fine.
Okay, fine.
And let me just say, if anyone has any pressing questions during the talk, I'm happy to engage along the way. I may not notice on the screen, so if there is any question, feel free to ask it as I'm speaking.
Okay, sure. Okay, maybe we should start. My name is Bhanu Das, and I'd like to welcome all of you to this webinar on quantum simulations and quantum. Okay, so can you hear me? I think.
Yes.
Okay,
Yes.
thank you. Okay. So I was saying, I'd like to welcome all of you to this webinar on quantum simulations and quantum computations with cold atoms. And so this webinar is jointly organized by the Innovation Hub of the Quantum Technology Foundation of India and the Center for Quantum Engineering Research and Education in Kolkata. I'm from the Center for Quantum Engineering Research and Education in Kolkata, which is one of the centers of TCG Centers for Research and Education in Science and Technology. Our center is about 1.5 years old, and the focus of our center is quantum science and technology, in particular quantum computing using trapped ions and superconducting qubits, also trapped ion clocks. And we also work on quantum algorithms of atomic and molecular properties, as well as climate modeling. I would now like to request Professor Umakant Rapol to say something about the Innovation Hub of the Quantum Technology Foundation, which is the National Quantum Technology Hub of India. So Professor Umakant Rapol, please.
Yeah, thank you, Professor Bhanudas. Yeah, and thank you, Professor Mark Saffman, for kindly accepting our invitation. So I'm an associate professor at IISER Pune, and we have recently, about 1 year ago, established this Quantum Technology Innovation Hub called as iHub Quantum Technology Foundation at IISER Pune. IISER Pune itself is about 15 years old, and this hub has been established under the auspices of the National Mission for Interdisciplinary Cyber Physical Systems of the Government of India, funded by the Department of Science and Technology. So this hub is going to concentrate mainly on 3 verticals in technology development and research on quantum technologies. The first vertical is on quantum information and metrology. The second vertical is on quantum communications, and the third vertical is on quantum materials. So we'll be working towards different platforms for quantum information processing, including atoms, ions, NMR systems, different kinds of solid state systems, including superconducting qubits and also NV centers. And all that is one part, and also on quantum metrology and quantum sensing, different kinds of platforms for various things, including atom interferometers and also NV centers and things like that. And we have a large group of people concentrating on developing the different kinds of materials with exotic properties, which come under the classification of quantum materials for various applications, including for futuristic quantum information processing devices. So thank you all for joining this exciting webinar. And I would like to request Professor Bhanudas to take this forward. Thank you all.
Okay, so thank you. Let me first of all say a few words of introduction for Professor Mark Saffman. So he's the first speaker today. As many of you know, Professor Saffman is one of the pioneers of neutral atom quantum computing. And it's indeed a pleasure and privilege to have him give the opening talk of this webinar. He is internationally acclaimed, for his work on, as I said, neutral atom quantum computing, and for at least a decade, he's been making seminal contributions to this field. He's a professor at the University of Wisconsin-Madison, and he's also the chief scientific officer of Kolkata, which is a startup at the University of Colorado Boulder. And under his leadership, both these institutions have made very important strides in the field of neutral atom quantum computing. I'd now like to request Professor Saffman to give his talk.
Okay, thank you, Professor Benadas, and thank you for the invitation to participate in your conference. It's great to see growing activity in quantum atomic technologies in India. In fact, one of the postdocs working with me in Wisconsin in my group is an Indian from India. And so it's great to build those connections. So I want to speak to you today about neutral atom quantum computing, and the organizers asked me to start with a little bit of an overview of what's going on, and I'll do that to a certain extent, and then tell you about some of the recent progress from my research group. And let me emphasize from the outset that the experimental results I'll show you are from the University of Wisconsin, but this has been part of a very close collaboration between the university and between Cold Quanta, who are developing a commercial version of what you'll see today. The background on the screen here is not just a cartoon, but this is actually real data of some new and as yet unpublished work scaling up these neutral atom qubit arrays to very large numbers. So this is just the central part of a very large array of trapped cesium atoms, more than 1,000 atoms trapped on 3 micron centers. And you see now a very regular, perfectly arranged array with uniform spacing and very good imaging of these atoms at high resolution. And this is part of the potential of this neutral atom approach to scale to very large systems, and with the right optical engineering in place, we can work with these systems with very high fidelity, as I hope I'll convince you during this talk. So moving on first with a little overview of the quantum information area, I think as everyone knows, there are a number of approaches that are being developed for quantum computation. And roughly speaking, one can divide the different approaches into several different categories. There are approaches using atomic qubits, so single atoms or single ions, in which we encode qubits and quantum states. And these atomic qubits are essentially perfect. We get them essentially for free, and they're all identical, and they have excellent coherence properties, and they can be controlled very precisely using combinations of microwave and optical frequency electromagnetic fields. Those atomic approaches can be contrasted with engineered qubits, which are not identical, and which require deep cryogenic cooling down to the millikelvin temperatures to provide long coherence time. So these are really two contrasting approaches, and I'm not going to say that one is any one of these is the only way to proceed. I think in principle, with continued development, all of these approaches will be of value for quantum computation over time. But each of these approaches has its own advantages and challenges in terms of scaling up and reaching high fidelity in these systems. There's also optics-based approaches using either single photons or squeeze coherent states. This is not the talk to go into great detail about the relative merits of all of these approaches in detail. depending who one talks to, either one's very excited about the optical approach or one thinks that the scalability of this approach is going to be challenging. I think we'll know more in the next few years. But today I really want to focus on the neutral atom approach that my group and many other groups are very actively working on. So let me continue with just a very brief history of the developments in terms of this approach towards quantum computation. Just over 20 years ago, the first proposals appeared for how to use neutral atom qubits for universal quantum computation. And those early proposals were made by some of the pioneers in the field. In the early 2000s, we started to see the first experimental demonstrations of quantum state control on single trapped neutral atoms from several groups using several different methods, either in optical traps or in resonant cavities. And close to a decade later, the first demonstrations of universal gate sets. So that's 1 qubit gates, 2 qubit entangling gates, and preparation of entangled Bell stapes were done by my group and the group around Philippe Branchet and Antoine Proet's near Paris. A few years after that, we started to see the scalability of this approach with arrays of up to about 50 controllable atomic qubits. And a few years later, a very important development in the field was the introduction of approaches for rearranging the atoms to create fully occupied quantum registers. And this was done in Korea, at Harvard, and the Lucan Group, and at the Institut d'Optique. A few years later after that, we entered what I like to think of as the high fidelity era, where, and this is still the highest fidelity entanglement in the field, better than 2 nines using strontium atoms by the Endres group at Caltech. And now just recently, we've seen the first demonstrations with atomic qubits of multi-qubit, multi-gate circuits, both here in Wisconsin and at Harvard. And I'll talk about our results in this area in the following. And what's next? Well, I won't put a definite prediction down, but I strongly expect and anticipate that sometime in this decade, we'll start to see really useful neutral atom quantum computers. And my own definition of useful is that these will be machines that non-scientists who are not experts in atomic physics and lasers and so on will be able to use these machines to solve some problems of real interest. So I think we're on the cusp now of really a very exciting time in this field. And this neutral atom approach relies on the properties of atoms and the properties of atoms when we excite them to Rydberg states. And so we'll be encoding quantum information in the hyperfine states, hyperfine clock states of neutral atoms. These have very long coherence times. And if we separate them by a few microns, they interact really very, very weakly. If I measure the interaction strength in frequency units, it's about 1 millihertz. And so that's great for quantum memory, but it's not adequate for quantum logic, because to perform computations, I need to get these atoms to interact with each other. And we do that by exciting the atoms to Rydberg states, where we can, and these Rydberg states have delocalized wave functions and therefore interact very strongly at that same few micron separation. And indeed, we're turning the interaction on and then off again with a contrast of something like 12 orders of magnitude. And it's this enormous contrast that seems to be quite unique to the neutral atom approach to quantum computation, and is in my mind, the critical enabling feature of this approach to quantum computation. And so with this ability to turn the interactions on and off, we have a single system where we can both isolate the qubits from the environment, which we need to maintain their quantum properties, and also control them, which we need to perform computations. So we have an array of these trapped atoms, trapped by light. They're extremely well isolated. Quantum properties can be maintained for seconds to minutes timescale. We then focus laser beams to individual atoms, excite them to these Rydberg states, and turn off this super strong interaction that has the potential for fast logic operations at tens of nanoseconds. I wouldn't say anyone's achieved this at the tens of nanosecond scale quite yet, although there's some interesting developments. And I think Professor Omori, who's up next, will also talk about their work in very fast control of these atomic systems. And this long, super strong interaction translates into a long range of interaction. So this plot shows another way of looking at that, where I'm showing the interaction strength versus the interatomic spacing in microns. The qubit encoded in the hyperfine states has this 1/r², very weak magnetostatic dipole-dipole interaction measured in fractions of a hertz. And then as we go to higher and higher Rydberg states, we get this longer range interaction. And if you think about the range of this interaction out to where we still have a megahertz scale two atom couplings, and think about that in terms of the distance relative to a qubit array spaced by a few microns, we have the potential for having very large connectivity together with large numbers of qubits. And so that's going to be enabling for quantum information. The experiments I'll show you in a few minutes are actually done at this point here. We're about 9 micron spacing and working at about 75s Rydberg state, which gives us a few megahertz of interaction, as I'll show you. And this point about connectivity, just to say a few more words about it, you can contrast this with, for example, engineered systems, which are hardwired with nearest neighbor connectivity or even less than full nearest neighbor connectivity on a fixed layout. And it's really the combination of gate fidelity and connectivity that's going to enable algorithmic performance, because quantum algorithms require connecting qubits that are not nearest neighbors on a grid like this. To move quantum states around, one needs swap operations, which can be decomposed into 3 C0 gates. And so having this long-range connectivity is going to enable more efficient implementation of algorithms and error correction. So with that kind of introduction, let me look a little bit more closely at the Rydberg blockade and identify a couple different regimes of operation. So imagine I have an array of qubits and I illuminate all of them with a laser that couples the ground state or one of the ground states up to a Rydberg state. And I simply illuminate all of the atoms in parallel with a plane wave excitation beam. And these atoms will interact when they're Rydberg excited with a van der Waals type interaction proportional to a C6 coefficient, and that will give a blockade distance, which is the ratio of the C6 coefficient and the rate omega at which I excite the atoms. And in the limit of weak interactions, that is to say the blockade distance is small compared to the lattice spacing, I'll simply excite all the atoms in parallel to the Rydberg state. That's not what we want for computation, but that's very useful for quantum sensors, actually, because these Rydberg states are tremendously sensitive to electromagnetic fields, not just the field I use to excite them, but other fields. And so these can be used for very sensitive quantum sensors. It's a subject of a separate discussion. Then there's a intermediate regime where the blockade distance is of order the lattice spacing. And in that regime, the atoms, when all excited by this broad beam, will self-organize themselves into an arrangement that minimizes the free energy, if you will. And so in this regime, spatial correlations will naturally emerge. And this was first shown by the Bloch group a decade ago in a seminal experiment that they did. And then there's the regime of strong interactions where the blockade distance is really much larger than the lattice spacing. And this is the regime of strong Rydberg blockade, so that just a single atom will be Rydberg excited. But it could be any one of those atoms. And if we think about this from a quantum perspective, what we're really preparing is a coherent superposition of any one of all atoms being excited. And this is a paradigmatic entangled state, a W state, where a single excitation is shared among all the atoms. And experiments in this regime have also been done in past years. And it's really some combination of these two regimes here that are of interest for digital quantum computation, but also analog quantum simulation using Rydberg atoms. So just to give a little bit of an overview, let's look more closely at the question of analog versus digital approaches using Rydberg interactions. So on the one hand, one has analog simulators, and there's been beautiful work done in recent years at Princeton by the Backer Group, at Harvard, at Institut d'Optique, where one excites all of the atoms to the Rydberg state and uses their interactions to implement Ising models in particular. And this type of approach has somewhat simplified control. It's partially programmable, but there's not a clearly defined path to full error correction for this system. That analog approach can be contrasted with the digital gate model circuits. So here's an example of a phase estimation circuit where we're directly controlling individual atoms, performing gate operations, and then here's a histogram of some output data. And there's very recent results on this from our group and also from the group at Harvard. And I think you'll hear about that from Giulia Semaghini towards the end of this workshop. This approach has full quantum state control. It's also more difficult to implement than the analog approach. It's universally programmable. And although challenging, there's a well-defined path as we improve the fidelity of the control towards error correction and full scalability with this approach. So digging just a little bit more into the analog approach, the type of simulation that's been done most widely is this quantum Ising model. And here's the Hamiltonian of the Ising model. There's three important terms. N here represents the excitation to a Rydberg state of an individual atom. If the atom's in the ground state, then N is 0. If it's in the Rydberg state, it's 1. So if two interacting atoms are both Rydberg excited, one has a two-atom interaction term with a strength U given by the C6 over R to the 6 van der Waals strength of the Rydberg interaction. Then there's an effective transverse field term, which is proportional to the Rabi drive, the rate at which the atoms are excited. So that gives effectively a sigma X term that transfers the atoms back and forth between the ground and Rydberg states. And then depending on the detuning of the Rydberg drive from the Rydberg transition, one has an additional local term proportional to that detuning and the number of excited atoms. So that's the quantum Ising model, which in a very natural way maps onto these Rydberg arrays. And this is interesting for a number of reasons. So 40 years ago, Barahona showed theoretically that the non-planar Ising model, or the Ising model with transverse field and long-range couplings, are NP complete models. So these are models in a complexity class that cannot be efficiently simulated in polynomial time. And so Rydberg analog simulators that naturally implement this kind of model and can do it with long-range coupling so that one can implement non-planar problems, these analog simulators may be able to tackle hard problems of interest. There's some open questions. What is really the level of programmability? Certainly the detunings and the Rabi drives can be made locally dependent. The Rydberg couplings can be controlled by the geometry, although unless one has individual control of pairs, one doesn't have full programmability of this term in the Hamiltonian. So there's questions about programmability. There's questions about depth of simulation, since one is using the Rydberg states that have a finite coherence time, and how does one eventually get to error correction? Nonetheless, there's been some really exciting progress implementing this model in the last year, both from the CNRS and Harvard groups who've used this to study quantum magnetism and phase transitions. It's also potentially very powerful for solving certain graph optimization problems, such as maximum cut and maximum independent set. And there'll be some talks in the next days of this workshop, really digging into what's been done with this analog simulation approach. So With that overview, let me proceed to the digital approach. This is a picture of my lab in Wisconsin. There's a lot of stuff involved, and it kind of reminds me of the old pictures of the ILIAC vacuum tube computers from the 1950s. This is how it looks today. I think in a few years, we're going to see much more compact, much more cleaned up versions of these kinds of systems. If one looks more closely at the core, the quantum processing unit, somewhere buried inside here is a small vacuum cell where we trap the atoms. And then there's a large amount of optics and beam scanning devices that go into operating the computer. So these experiments can be done with a variety of different atoms. The majority of the work to date has used the heavy alkali atoms, rubidium and cesium. In Wisconsin, we're using cesium atoms. There's also very significant progress in the last few years with the alkaline earth atoms and both strontium and ytterbium. And these are particularly interesting because these are also optical clock atoms. So one can combine the entanglement capability of quantum circuits and Rydberg interactions with the pristine transitions that enable optical atomic clocks. But let me proceed with the cesium atom that we use. I think of this as an industry standard qubit simply because the international definition of the second is based on the energy separation of those two m=0 clock states. And those are exactly the same states we use for encoding our qubits. These states are themselves entangled superpositions of the nuclear and electronic spin projections, but not the type of entanglement that's useful for quantum information. These states have excellent coherence properties, many years in free space, and when they're optically trapped, coherence times up to tens of seconds have been demonstrated. The coherence is limited by atomic motion at finite temperature, differential shifts from the trapping optical fields, differential Stark shifts, any magnetic field noise. Using magic techniques, it does look like minute scale coherence is going to be possible with further engineering of these systems. So that's our qubit. And then to turn that into part of a quantum computer, there's a sequence of operations. And I like to divide those operations into two groups. The first group is where we control the mechanics. That is, we do laser cooling to create clouds of cold atoms at tens of microkelvins. We then load those atoms into a trap array. We do another stage of deep cooling to get down below 5 microkelvin. And then we use rearrangement techniques to create fully occupied registers. And then there's the sequence of operations to actually run quantum gate circuits where we prepare an initial clock state using optical pumping. We run through the gates defining the quantum circuit, and then we measure the output results using light scattering and imaging with a camera. So let me speak first to the mechanical aspects just briefly. When one looks at optical trapping, there's really two types of traps we can use. There's red traps, where the atom is attracted to a region of maximum intensity. And this is most directly done just with a focused TEM00 laser beam, so an optical tweezer trap. And we use these types of traps for atom transport and for filling the register. And then for the actual computation and circuit operation, we put the atoms in blue traps. And the blue traps use light with a frequency higher than the strong optical transition. And so this gives a repulsive potential. So the atom becomes localized at a region of low intensity. And this is good for holding qubits for a long time with minimal disturbance from the trapping light. So we get the best possible coherence properties. And my group over the years has investigated a number of different designs for making arrays of these blue traps using bottle beams, arrays of bottle beams, weakly overlapping Gaussian beams. What we've been using most recently for circuits, we call a dynamic line array. where we prepare a grid of blue detuned light. And so the atoms are essentially trapped in cages. And out of the plane, the lines spread due to diffraction. And so we actually get a two-dimensional array of three-dimensional blue detuned traps. And we've trapped up to several hundred atomic qubits in systems like this. This type of line array using acousto-optic devices is dynamically controllable. And we made arrays large enough to hold up to 500 sites. And then most recently, we've been working with yet another optical approach that we call a whole array. And I don't have time to go into details, but it's a combination of a fabricated component and some Fourier filtering, which can be used to create an array of dark traps, so blue detuned traps. And this is what we've used to trap over 1,000 cesium atoms in a very regular grid. Another advantage of this kind of blue trapping is that you can trap both the qubit, but also the Rydberg states that we use for interactions. And so the Rydberg states you can think of as free electrons with a negative polarizability, and they're trapped in the same optical landscape as we can use to trap ground state atoms. And so one can see the difference in the population lifetime of a Rydberg state, in this case 61D, with the trap on versus the trap off, accounting for spontaneous lifetime. This data corresponds to a mechanical trap lifetime of more than 300 microseconds, much longer than the sub-microsecond gate times we use. So that's a trapping approach, and then we add to that atom rearrangement, which most beautifully was demonstrated by the Broays group, creating an atomic Eiffel Tower. I never cease to be amazed by the beauty of this demonstration. We're doing this in 2 dimensions, and so we can write out letters, for example, and put the atoms where we want for circuit measurement. And then the final mechanical step or final capability we need before getting to the logic gates is the state measurement, which we do by imaging scattered light onto a camera and generating histograms that distinguish between atoms in a dark state and atoms in a bright state that cycled up to the first resonant transition of the atom. So that's the controlling the mechanics, if you will, and also the measurement. And then there's the calculation cycle involving initialization, gates, and measurements. And we do that in this geometry here. We have a small vacuum cell. We're imaging from both sides to get more light. Those images get transferred over to a EMCCD camera. And then we have several acousto-optic beam scanners, one for the atom rearrangement, which is a 1064 nanometer laser, and then a scanner for the blue light and a scanner for the infrared light for 2-photon excitation of the Rydberg states. And this system was designed and fabricated in close collaboration with the Cold Quanta team. Here's a CAD picture, and at the core of this is the pristine vacuum technology that Cold Quanta is superb at, within which we trap the atoms. And these vacuum cells also have electrodes for controlling local field environments. So putting all the pieces together, it's a lot of laser technology. There's something like 6 different colors and more than 10 different laser systems to implement all the control that's needed. And doing that, we arrive at a gate set for the quantum control. We're encoding in the clock states of cesium atoms. And then our gate set consists of a few components. We can globally rotate all of the qubits using microwaves. And this can be a rotation about any angle in the XY plane of the Bloch sphere by controlling the phase of the microwave. We perform single-side, single qubit gates by combining the microwave with the focused laser beam, giving optical Stark shifts, and I'll show you how that works in a moment. And then the Rydberg blockade gives us a controlled Z gate, which combined with local rotations gives CX or C0 gates. So here's some old data, excuse me, showing global rotations using microwaves. This was with a microwave frequency of about 10 kilohertz, and we achieved gate fidelities as determined by randomized benchmarking above 2 nines of fidelity. So this was work from back in 2015. We're doing essentially the same thing today, except we put in place a more powerful microwave amplifier, which boosted the Rabi frequency, and we're now significantly higher fidelity for these operations, close to 4 nines. So again, doing randomized benchmarking here on a 49 site array. These are the spam errors, state preparation and measurement, which average about 3% across this array for this data set. And the average fidelity of the Clifford gate set is just shy of 4 nines using the microwaves. The single site operations are implemented by adding a focused laser beam targeting an individual site that gives a stark shift at that site. And so if one takes that focused laser beam, which gives an RZ rotation, and put that in between 2 microwave pulses, which are implemented with equal pulse areas, but opposite phase, so a pi by 2 and a minus pi by 2 pulse. If there were no RZ, the pi by 2 and minus pi by 2 would cancel, nothing happens. By inserting an RZ, we get an effective RX or an RY or anything in between gate. So we can do local rotations in this way. And again, we've characterized those now just on a subset of the sites, which we've used for circuits in the first instance. Again, the spam errors are between 2 and 3%. And then the I'm so sorry, I had a power problem here. Am I back?
Yes.
Okay, let me share my screen again. Okay, go back to where I was. Let's see, I need to get into, there we go. Okay, okay, I was talking about the local gates. I see I need to speed up a little bit. Let me see if I can turn my pointer back on. Okay, this just shows the ability to focus the laser beams and rotate individual sites without crosstalk on the neighboring sites. We can also do this in multiple sites by putting multiple tones on the acousto-optic scanners. And this shows the corresponding ground Rydberg operations on local sites where we can turn this atom from bright to dark. And then the all-important 2-qubit gates, we're doing this with Rydberg 75S states. And we've done this in 2 ways, using a larger beam, about 7 microns waist, that illuminates 2 atoms simultaneously, and then using focused laser beams, which is what we use for circuit operation. So this is a pair of atoms at 9 micron spacing and 3 micron beam weights. And you see the populations and the parity curves. And using the protocol from the Harvard group from 2019, we can address both strongly interacting atoms closely spaced with about 1 gigahertz of Rydberg blockade in this configuration, and just a couple megahertz of interaction in this configuration. So this is really not a blockade gate, but a weakly interacting Rydberg gate. And we've been able to push the Bell fidelity up to about 95.5%. So with all those capabilities in place, we've been climbing up this prickly hill, if you will, and we're now ready to start using the system to look at quantum algorithms. And so in the remaining minutes here, I'll show you some of our recent work demonstrating quantum algorithms with this system. And long term, to realize the full potential of quantum computing, we know we want scalable, error-corrected systems. We're not there yet, but it's very fruitful to explore what we can achieve pre-error correction. And I'll show you some results on quantum circuits we've been running. And in particular, hybrid algorithms appear to be a possible path to quantum advantage, even before we get to fully error-corrected systems. So as a first test, we used the quantum circuit to prepare a multi-qubit entangled state, a maximally entangled GHZ state. And those states can be prepared by a cascaded sequence of C0 gates connecting a register of qubits. And so here you see some data using 6 sites selected out of the larger array. And by running gate sequences between those sites, we're able to create n equals 2 up to n equals 6 maximally entangled states. Here you see the fidelity of those states, the raw data, and then spam corrected. And as we go to larger and larger states, the fidelity goes down because the gate imperfections accumulate. But the spam corrected data looks like it's going to cross the threshold for entanglement at about n equals 8. These are relatively long-lived entangled states with coherence times of a few milliseconds. This is just the intrinsic T2 star of the qubit. Using dynamical decoupling, we're able to push the T2 up to about a second. And we're currently looking at using dynamical decoupling on the GHZ states to get both the enhanced phase sensitivity of the entangled state together with a longer coherence time, and investigating what can be measured with that type of approach. So that's the first example showing circuit operation on the qubit array. We then moved on to the phase estimation algorithm. Quantum phase estimation is one of the most important quantum algorithms. It's useful for quantum chemistry, and eventually also plays a central role in Shor's factoring algorithm. And in quantum phase estimation, one has a register of qubits which represent the phase, and then there's a second register where one implements the unitary operation corresponding to a Hamiltonian of interest, using exponentiation of that unitary operator to ever increasing powers. That phase corresponding to the unitary evolution is effectively mapped onto the qubit register, and then one implements a quantum Fourier transform to represent that extracted phase as a maximal population in a particular qubit, which can then be read out by measuring the register. And so here's a first example of that with where we just verified that we could measure phases of 0, pi by 2, pi, and 3 pi by 2, which can be, those phases can be exactly represented with 2 bits in the measurement register. So it's a 3-bit circuit, implemented different unitaries on the 3rd qubit corresponding to those phase advances. And indeed, you see the 0 phase corresponding to the identity operator, pi by 2, pi, and 3 pi by 2 in these histograms, where the dark blue is the experimentally measured data, and the light blue is what one would have with perfect circuit operation. We then went on to a more complicated version of that, which implements a reduced model of the hydrogen molecule. So this is a Hartree-Fock Hamiltonian for H2, and we implemented a trotterized version of this as our unitary operator here. And so there's a part of the circuit is to do the phase measurement on this unitary operator, and then there's the inverse Fourier transform operation and the readout. For this Hartree-Fock approximation, the input state here is not an exact eigenstate of the unitary, and it has partial overlap with the two eigenstates of this operator. And so you see finite population in these two bit strings. One of them gets about 80%, the other about 20% of the probability, and the dark blue showed the measured circuit results. Again, this is somewhat noisy. These are deep circuits involving about 15 C0 gates, and so errors do accumulate, but we do see a maximal probability coming out of the circuit corresponding to the maximum predicted probability for the eigenstate of this operator. And then the last type of circuit we went to was a hybrid circuit, the QAOA algorithm for the max cut problem. And you can think of QAOA as a, if you like, a trotterized version of adiabatic evolution, where one alternates between a mixer Hamiltonian, which applies an X rotation to all qubits, and a problem Hamiltonian, which implements the computational problem of interest. And the circuit is, in addition, has classical weights, beta and gamma. And by choosing those weights appropriately, one can drive the state coming out of the quantum circuit to a state which minimizes the cost function or energy of this problem Hamiltonian. And so the classic example of this is introduced by Farhi and Goldstone, is applying this to the max cut problem, where this is a graph, combinatorial graph problem, where one seeks to divide a group of nodes that are interconnected into two classes, which maximizes the number of connections that go between nodes in opposite classes. And you can map that onto this Hamiltonian, which is the product of z's on connected nodes -1. And so if the nodes are in the same class, this will give you 0. If they're in opposite classes, this will give you a -1 here. And so this Hamiltonian will drive the system to the ground state, which maximizes the number of cuts. And so here's an implementation of that on a 4-node graph, where a central qubit is connected to 3 surrounding qubits. The max cut solution has the central qubit in the opposite state of the other 3. And so the way we've mapped this onto our bit strings, the solutions are 0001 and 1110. And then we ran this for multiple rounds of the circuit. So p = 1 would be just doing this once, and then we can continue doing it more times with appropriate classical weights. And the approximation ratio is a measure of how close we are to the ideal result. And we get about 67%, 69%. And then when we go to p = 3, the result starts getting a little bit worse again because of accumulation of noise in the circuit. This p = 3, this is a relatively long circuit with 18 CZ gates and a large number of local operations. So just to wrap up, actually one more thing about QAOA. Here we see accumulation of gate errors in what I just showed you. There are ways that QAOA can be generalized, for example, by replacing this mixer Hamiltonian with arbitrary rotations in the XY plane. Some recent work that we were involved in shows some examples of this, and generalizing this mixer Hamiltonian, one can get much better performance even with finite gate fidelities. And that's something we're also looking at this time. What's the outlook? Well, the 2-qubit gate fidelity is critical for improved performance. A lot of different protocols have been implemented. Perhaps the most elegant and simple protocol is just a simple adiabatic pulse connecting ground to Rydberg states. And this protocol was introduced by my group in Wisconsin and also independently by the group in Wuhan, who have also implemented this in the lab. And rigorous analysis of this type of protocol shows that fidelity well above 3 nines should be possible using this type of single pulse gate. And it's interesting to look at what the status actually is at this time for 2-qubit entanglement experiments with Rydberg atoms. This table here shows the experiments from the last couple of years. What we're doing using cesium atoms. This is in a 2D array with tightly focused control beams. Raw fidelity is about 0.93, and correcting for spam errors, we see fidelity about 0.96. The work from Harvard with rubidium atoms is about 0.95 raw, 0.97 spam corrected. These two experiments use the same protocol, which we took from the Harvard group. Experimentally, we're using tightly focused beams. They're using very large beams. There's also been a recent work from the Wuhan group using this single pulse adiabatic protocol, which actually has achieved the best result to date in terms of a spam corrected 0.98 fidelity. Also, this experiment used what I'd call medium-sized beams, about 7 micron waist beams. And then there's also been the strontium experiment from Caltech, again using large beams, but these were not long-lived qubits. These were ground Rydberg qubits, so this is a relatively short-lived entanglement, but they were able to push that up to the 99% level. So, multiple experiments are now above 95% fidelity. The current limitations are very much still technical, and it's clear that for improved fidelity, we need colder atoms, better control of the optical beam profile, low laser noise, and higher power to reduce photon scattering. These are engineering challenges, not science, and I think we're going to see significant further improvement in these numbers in the next year or two in this field. So then to conclude, let me remind you that I hope I've convinced you that neutral atom qubit arrays provide a scalable platform for quantum computing. We're now able to operate circuits in these arrays with gate fidelities that range from almost 4 nines for single qubit global gates to above 95% for 2-qubit entangling gates. We've demonstrated a couple of basic quantum algorithms with this system and are continuing to expand the capabilities. And a better engineered version of what I just showed you with higher performance is going to be available over the cloud later this year from Cold Quanta. So let me stop there and thank you for your attention.
Okay, thank you, Professor Saffman. So if you have any questions, can you put it in the chat box, please? Questions or comments?
I see a question about references to understand the decoherence related to the hyperfine levels in the Rydberg states.
Yes.
So there are certainly papers in the literature from the last couple of decades. I might also mention a recent book on quantum information that I co-authored with Mark Hillary and Shanos Burgo, has a full chapter on atomic qubits that also talks about decoherence issues in detail. So you might look there.
Okay. So I think there's a comment by, so Arup Bhomik says he has a couple of questions. Can he unmute and ask directly? Okay, please do that. Yeah, Arup Bhomik, yeah.
Hi, Mark. So I have a couple of questions. First of all, I want to know what's the lattice constant of your array, because when you are doing this Rydberg excitation, am I audible? First of all,
Yes, I hear you.
Yeah. So what's the lattice constant you are using for?
Sure. So this array here,
Yeah.
the spacing is 3 microns, although to minimize any residual crosstalk from the focused laser beam, which is also about 3 micron waste, we're not using every site. So we're using every third neighbor for the circuit demonstrations.
Okay, because what I understand is you are exciting to the n equals to 75, where your blockade radius is around 9 micron, right? So it will cover 9 micron blockade radius. I mean, all the atoms inside the blockade, right? So there will be there is a possibility of cross-talking between 9 microns. That's why, that's the reason, right? Yeah, please.
Well, I mean, just to be clear, so we implemented gates at 9 micron separation, but we're doing this with focused laser beams much smaller than 9 microns. So we're selecting pairs of atoms to excite at one time. So these blue lines here show the gate connections that have been implemented.
Okay. And secondly, what I want to ask is, like, when you are having the Rydberg excitation, then your Rabi frequency, effective Rabi frequency, it's a 2-photon excitation. So you'll have an effective Rabi frequency. It will scale as root over number of blockades time and a number of atoms inside the blockade time the single excitation Rabi frequency, right? So that's how you are, I mean, you can estimate how much atoms are participating in a single blockade, right?
Well, yes, one can, but so perhaps this is not completely clear. This is the array if we fill it.
Yeah.
Okay.
Yeah.
But for example, for this phase estimation algorithm, what we did is we used rearrangement to only populate those 4 sites. Okay. And then we, using focus beams, just address 2 atoms at a time. So for these circuit demonstrations, there's no root n scaling of Rabi rates where n is the number of atoms. We're just selecting 2 atoms at a time.
Okay.
So I think we'll move on to the next question, please. So there's a question from Umakant Rapol. What is the maximum 2-qubit gate execution time that has been achieved?
So these gates, the 2-qubit gate in these circuits, I think the time was about 3/4 of a microsecond, so 750 nanoseconds. The shortest times so far have been around half a microsecond. Theoretically, we've been able to predict very high fidelity at gate times as short as 50 nanoseconds, although that's not been done in the lab yet. But I think there's an outlook once we get the appropriate lasers in place to do this on very short timescales, around 50 nanoseconds.
Okay, so there's another question from Umakant. Will using a dynamically variable lattice constant reduce addressing errors and crosstalk?
Yes, and this is perhaps a little bit in the spirit of what the Harvard group has been doing, which, I mean, in our approach, we're moving the laser beams around. The atoms are fixed, we move the laser beams. You could also flip that on its head and say, have the laser beams fixed and move the atoms around. So, our perspective on this is that we can move laser beams very rapidly at 100 nanosecond kind of timescales. If you want to move the atoms around, either using tweezers or by dynamically reconfiguring the lattice, you can't do that too rapidly without decohering the atoms. And so that gives you a much slower circuit operation. So yes, that's potentially a potential approach, but we think moving the light around and keeping the atom stationary is a better approach in terms of reaching high clock speeds and more scalability.
Okay.
Thanks, Mark.
Okay, so the next question is from Thierry Lahai. Beautiful results. I was wondering what power is needed to make those large blue detuned arrays, for example, with 1,000 traps.
Sure. So for that array, we're using about 10 milliwatts per trap. So for 1,000 sites, that's 10 watts. So we actually made that very large array using a multi-mode laser diode bar. So we can use a relatively inexpensive, off-the-shelf laser component to make a very large array. But ultimately, you need a certain amount of optical power per trap, and so the larger the array, the more optical power will be needed.
Okay, so there's a question from Sri Ganapati Raghav. How do you address the decoherence due to the high frequency laser used for engineering the lattice? That's the first question.
Sure. So we're using low noise lasers, Ti-Sapphire, single frequency Ti-Sapphire lasers, and we can add noise eaters using acousto-optic modulators to reduce any residual intensity noise on those lasers.
Okay. Then the second question is, will there be coupling to higher energy states when you prepare an atom in a Rydberg state?
So certainly the light that couples the ground state to the Rydberg state also couples the Rydberg state to the continuum. And at some rate will photoionize the Rydberg atoms. If you do the atomic physics calculation and look at the rates for that, that's a completely negligible contribution to the gate fidelity. So that turns out not to be of concern. Okay, so I think we should move on to the next talk. So I'd like to thank Professor Saffman for an outstanding talk. Thank you very much. Thank you, and thank you very much. Yeah, bye. Okay, bye. Okay, so. Okay, so now we'll move on to the next talk. So that's by Professor Omori. So is Professor Omori there?
Hello?
Yes, okay, Professor Omori. So yeah, all right. So, okay, so the next talk is by Professor Omori, and I'll just say a few words of introduction.